So, the component object model is this thing that lets you take internal components from software and then share them over the network, which is convenient if you want to sell your software and has appalling security implications frequently. But anyway, if you want to use COM objects, you have to call OLE initialize for object linking and embedding, or co-initialize EX, and then call COM libraries. These things are accessed by globally unique identifiers, which are 128-bit odd numbers, and there are many different kinds of these things: class IDs, interface identifiers, and so on. These long things that look sort of like IPv6 addresses, and Microsoft uses them to refer to these objects. Exceptions are what happens when the processor cannot continue because you try to do something bad, like divide by zero, or jump to memory that you're not allowed to access, or jump to execute an instruction that is in non-executable RAM, or try to execute a kernel level instruction when you are in user land and you don't have the privileges. If any of these things happen, it triggers an exception, which will go to the Windows operating system and be resolved by Windows deciding if it's in user land, it will open up the default debugger, which used to be Dr. Watson, now might be WinDebug. If it's in kernel land, it cannot do anything except give you the blue screen of death. But you can choose to capture those exceptions in your own software, which is what a professional programmer will do. Like I say, hackers write this sleazy stuff that crashes when something goes wrong. Pros write stuff that catches every possible bad condition and returns an error message helping you fix the problem. And in this case, they want to catch these exceptions too. If somehow something tries to go to an inaccessible part of memory, then catch it and offer the user some choices, like how about we restart or update to the next version or something. Well, the structured exception handler is where this is, and this is stored in a FS segment of memory at location 0. And you just have a series. This just pushes an address and then loads it in a place. There are 6 segment registers. FS is one of them, and this is what the exception handler looks like. And you'll see it later on in Immunity as just a series of pointers where to go, and all you have to do is overwrite these locations and then trigger an exception, and you'll run your code. It's another way to get to code. And I mentioned before, kernel versus userland. The Intel processor supports 4 privilege rings. From 0 is the most powerful, and 3 is the weakest, but nobody uses 1 and 2. They are useless appendixes. Neither Windows nor Linux use them, so I don't know why they're even there. But anyway, so user mode on the outside. See, what this means is there's something like 10,000 instructions in the Pentium 4, and now we're up to the i7 and so on, it's probably even more. And some of those instructions are specifically considered dangerous and restricted to kernel land, because they directly connect to the hardware. User land can only use the other instructions. So in user mode is where everything you write goes. Microsoft Word and browsers and all the apps people write live in user land, and if they want to talk to the kernel, they call the Windows API, which goes in kernel land. Unfortunately, everybody that builds hardware, like network cards and printers, has to provide a driver for their hardware, and that driver has to run in kernel land. And Microsoft is very, very, very irritated by this. Many people got mad at all the blue screens of death, like Windows 95 and Windows 98. So in Windows XP, Microsoft made this system that would send information back to them every time Windows crashed. And they accumulated millions of those things, and they said 80% of the blue screens of death are caused by third-party device drivers. Those idiots that make the cheap stuff you buy from China just take their driver for Windows 95 and change the label to say, sure, it'll work fine in Windows 7, and send it to you. And it sort of works, and it sort of dies and crashes. And they've been ever more increasing this system where they want you to send your driver to Windows and have them test it and pay a fee, and then they will give you permission to put on the box designed for Windows 7, designed for Windows 8, and then it really won't make it crash, supposedly. But you can charge another 10 or 20 bucks for it, and so if you buy the cheapest stuff, you're getting these crappy drivers on floppy disks that have not been tested by Microsoft and will cause it to crash. But anyway, that's the game here. So all your code is in user mode. So each process has its own memory. And of course, if a user mode process crashes, it doesn't kill the whole machine. The kernel's still running, the other processes can go. This is why Google Chrome is considered to be more stable. Google Chrome is kind of a memory hog, but every tab is a separate process, supposedly. So if one tab crashes, the others won't. When Google Chrome was new, I tested this, and at that time one would go in and it would bring down all the others. Supposedly this feature actually works now. It didn't really work in the first few versions of Chrome. Anyway, that's the game here. And so if user mode program crashes, since the kernel is still running, you can just reclaim the resources and carry on. That one window's gone. You can go back and use your other windows. All right, so you cannot jump directly from user mode to the kernel. You do it with sysenter, syscall, or int2e. These use lookup tables to find predefined functions in the kernel. So you're not just jumping to an address in the kernel, you're going to an interrupt list, going to specified addresses that Microsoft wants you to go in the kernel. So all kernel processes share resources and memory addresses. And in fact, I could not believe this when I first found out, but when I took my hacking class, we went through the IP version 6 attack. If you send router advertisements to this thing, Kirk and I spent a few years going through every version of this, you can kill Windows dead with the blue screen of death by just sending a lot of network packets that cause it to generate IP version 6 addresses. And that's because in kernel mode, memory management is not done very well. You launch something, it just launches it, and if there's not enough memory, it just dies. The same thing's true, by the way, of an iPhone. You launch an app, and it just sometimes dies. And I say, why don't they fix it? And people tell me, you can't. There is no way to query to see if there's actually enough RAM before launching your app. You just have to start it and see if it dies. And anyway, that's the way the kernel is. I couldn't believe this, but that's really true. So this attack, a lot of people got mad when I demonstrated at conferences and stuff because it's not, in some sense, it's not very important because it's not exploitable in the sense you can turn it into a remote execution. It's just using up resources, but it was, I couldn't believe it when people told me this, and I asked enough smart people, they said it really is true in the kernel, there is no allocation of resources. A process starts, and if there's not enough memory, you get the blue screen of death. It doesn't limit it and somehow make it wait or something, which doesn't make a lot of sense to me. Anyway, antivirus software and firewalls also run in kernel mode, and as Tavis Ormandy has spent the last 5 years proving, antivirus software is about the crappiest stuff on earth. It's just incredibly bad and full of terrible security flaws. So his point has been sort of that you should be aware that running antivirus is not necessarily as much of a positive thing as you've been led to believe. Anyway, so you can put malware in kernel mode. That would be awesome. Then you'd really have that box. This is where rootkits tend to live, in kernel mode. And now no user-land program can clean them or detect them. And most malware does not run in kernel mode. It's content to run in user-land mode. It's the most advanced stuff that runs in kernel mode, which is hardest to get off. All right. So there's the native API. Now this is more nasty tricks, like raw sockets, like Berkeley sockets. There are two APIs in Windows. There's the low-level one, intended only for internal Microsoft use, and then there's the higher-level one, intended for public outsiders writing programs. So this is how it works. You got your application up there, like Microsoft Word or Chrome or something. Then it calls kernel32.dil. That is the normal API to run kernel routines that you're supposed to use. But all that does is call ntdil.dil, which is the internal Microsoft API that really does the work, and that goes down to NTOS kernel, which are the kernel functions, and runs it with, and does whatever it needs to do with drivers and such down here. So if you're a nasty malware writer, you can, of course, just skip over kernel32 and call the ntdil directly. Now that means, just like calling Berkeley raw sockets, you're going to have to do more calls to get the job done and more parameters, but it also means that antivirus and malware analysts and everybody looking for normal calls to kernel32 are not going to find them, and they're not going to know you're messing with the kernel unless they understand that you can use these native functions. These things are also not documented. This is another thing. An enormous number of people have figured out how to use undocumented Windows functions. The TechNet and everything only goes so far, and there's a bunch of internal stuff, either through a sense of security or just through an inability to bother writing all the documents. They're not known publicly, but the malware authors either figure them out or they get leaks from inside Microsoft or something, and they find out. So the native API is undocumented, and you can run anything that way, and the calls will look screwy. So here's some common native API calls: query system information, information process, information file, and so on. These will give you a lot more information about what's in the machine than the actual Win32 calls. Just like if you're a normal user and you want to adjust your experience, you are supposed to use Control Panel. And Control Panel will let you change the background image and stuff. But if you go into the registry, you can change hundreds of more things that are not in Control Panel. But you do it at a cost because you can also trash the whole machine. And the same thing's going on here. But the native API, you have more power, but more responsibility. So here's NT continue to return from an exception. You can use that to transfer execution to unexpected places and make a program difficult to debug. You can make it so your program keeps crashing and going to the handle and returning somewhere else. So you end up going from here to there, but there is not a call or a jump going from here to there. This will help keep people confused. When we get towards the end of the class, we'll go through some anti-disassembly techniques, and those are really evil. You can mess up your assembly code so that the disassembler cannot understand it, and the debugger cannot understand it. So that's good, clean fun. Anyway, all right. So I'll list the last one of these. All right. So what item do you reference with SC? All right, I guess I'll quit at 30. All right, that's service control. A popular answer, good. All right. So, what do you prepare with Olay initialize? However, I had to use these Olays when I was working in an escrow agency to connect Excel objects to Word objects. Object linking and embedding is how you did it back then. Anyway, I'll quit at 30.
Between the office products?
Yeah, 2 different office products, yeah. I remember when it was the sexiest thing in the world to actually put a spreadsheet in your Word document and have the letters wrap around it, and that was awesome. Everybody was amazed. When I started, you just had to print them out on paper and take Scotch tape and tape it together. There was no way to mix 2 programs together. Olay was one of the earlier technologies to do that. Anyway, these are COM objects. All right. I made my thesis. We did it by just cutting up paper and taping it together. All right. So where's the SEH? You tape the image on the page and then you Xerox it. That was how you did it. That's also how they lit up newspapers at that time, and you could look at them and see if the headline was crooked and stuff. All right, so this is exceptions. That's the structured exception handler. That's what it stands for. All right, and you'll get used to playing with it. We'll be, in the exploit development class, we'll be making attacks with it. You'll see it here too. All right, what ring causes the blue screen of death? People get such an attitude about a blue screen of death. Microsoft recently changed it to look more friendly, like the Apple one, that when it dies, like a smiley face instead of the text. There was a time when they had the red screen of death in Vista Beta that was more evil than the blue screen of death. And there was someone that started a really popular thread of jokes of Microsoft selling advertising space on a blue screen of death, which they did not really do, but the idea was kind of funny. Anyway, so that's ring 0. One ring to rule them all. All right, so anyway, all right. And which ring is not used by Windows?
I think the rings were originally part of a CS paper, and so that's why there's 4 of them.
Of a what?
Some CS paper.
So, yeah, I think there was an operating system, Mutex or something. Not Mute. Sorry, but M, MIPS or something. There was M something that actually used this stuff.
It's not OS2.
Knoppix?
Knoppix sounds like an OS.
Knoppix was actually Unix. I don't think they used it.
There's a whole bunch of flavors of Unix.
Yeah, I don't think any of them use it. Well, I could be wrong. It'd be interesting if they do. Anyway, it's more than one. Rings 1 and 2 are not used by anything I'm aware of that's important anymore.
Yeah.
But there was some time. There was some time when somebody thought that would be great.
Mm-hmm.
I'm not sure how much security you'd really get by cutting everything into 4 levels of security, but anyway, you can't do it. So let me turn off the recording and we'll see who won. The recording is here. This is chapter 7. If I can ever get to the right place. There. 126, chapter 7b.